let's talk about graphing polynomials. The first thing we're going to talk about when we look at how to graph polynomials quickly is power functions or endpoint behavior. So in order to illustrate that, let me leave my whiteboard app and show you a couple of graphs in Desmos. So try not to look at all of the functions I have that we're going to look at the graphs for on the left-hand side. Right now, let's just look at x to the sixth. And if you've been doing any graphing in your algebra class, you've probably graphed parabolas at least a couple of times. And what you should notice about x to the sixth is it looks really similar to x squared, y equals x squared. And the reason it looks so similar to y equals x squared is because the degree, or the biggest exponent you see, is an even number. In this case, the degree is 6, and that's an even number. So this is going to resemble y equals x squared. Now, if we compare this graph to, say, something slightly more complicated, x to the sixth minus 3x, so now we have that there in blue, that is going to look a little different. But what I want you to notice about that graph is the end behavior. What is it doing on the left side and the right side of the graph? And on the left side and the right side of the graph, the x to the sixth and the x to the sixth minus 3x are really similar. They're both going up to the left and up to the right. Okay, if we manipulate that a little bit more, and in green, we graph x to the sixth minus 3x squared plus 5x. So in green, what's happening in the middle of our graph, where it's dipping down into like y equals -7 and so, is different than the blue and the red. But what's happening at the endpoints is the same. It's going up on the left and it's going up on the right. And if we mess this up even more, x to the sixth minus 3x to the fifth plus 5x squared minus 1 in purple. To clean this up, I'm going to get rid of a couple of these other graphs. Now that dips really far down. Let me zoom out to -20. But what's important about this x to the sixth, since x to the sixth is still the most powerful function there, or most powerful part of our function rather, then on the far left and the far right of our graph, it's still behaving just like our original red graph of x to the sixth. So to look at what a polynomial is behaving like on the left and the right side, all we need to do is look at the first term, the term with the biggest exponent. Now, before we change the exponent from an even to an odd, I want to show you what happens if we make our leading coefficient negative. So here's positive x to the sixth, and if we graph for comparison negative x to the sixth, instead of going up on the left and up on the right, we now go down on the left and down on the right. And if we play with that graph a little bit, say negative x to the sixth minus 3x to the fifth in red there, zoom way out. In the middle, it's different, but on the far left and the far right, that graph behaves just like negative x to the sixth, down on the left and down on the right. And if we manipulate the middle of the graph even more with a negative 3x to the fifth and a positive 5x squared minus 1, none of those exponents are as big as a 6. So that blue graph is really similar to the negative x to the sixth that we started with. It goes down on the left and down on the right, but it's different in the middle. So if you have an even exponent for our biggest exponent, the left side and the right side will go the same direction, up on the left and up on the right, or if it's negative coefficient, down on the left and down on the right. Now you might be able to predict if we're dealing with odd exponents. Let me zoom in a little bit more here. 2x to the seventh. Now that 2, positive 2, isn't going to change our graph much, but notice now that we have an odd exponent, the x to the 7, the graph looks just like x cubed, really similar to x cubed. It starts off on the negative side on the left and goes up to the right. So down to the left and up to the right. If I manipulate more terms, so on the 2x to the 7th, but make sure that all of those exponents are smaller than 7. So 2x to the 7 minus 3x to the 5 plus 5x squared minus 1. In purple, the middle of the graph changes, definitely, but the graph still goes down to the left and up to the right, just like the power function, just like the 2x to the 7. If we change the sign of the 2, then our graph doesn't look like x cubed anymore. Now our graph looks like negative x cubed with a reflection. So it goes up to the left and down to the right. And you might not be surprised by now, as long as the terms I'm adding after the negative 2x to the 7 all have exponents smaller than 7, the middle of the graph may change, but it will still go up on the left and down on the right. So that very first term we see is a really important part of our graph. It's what we call the power function. So let me capture that before moving on. Power functions. If you have a power function, let's say that for the largest exponent, which by the way is the degree of the polynomial, if that largest exponent is even. Oops, let's clean this up just a little bit. There we go. So if our degree is even, say for example, f of x equals 3x to the 4th. Then the graph will go up on the left, don't know what it does in the middle, and then up on the right. If we had, let's say g of x is 5x to the 4th minus 2x, that graph might change in the middle. The middle might go up and down, but on the far left it will be going up, and on the far right it will be going up. It'll go up here, don't know what it does in the middle, and it'll go up over here. If the degree is even and you have a negative leading coefficient, negative 3x to the 4th, that graph will go down on the far left and down on the far right. And I know this one hits at 0 and goes back down, but if I had, say, g of x is negative 3x to the 4th plus 7x minus 1, I might not know what happens in the middle, but I know because my degree is even, because I have a 4 here, and because my leading coefficient is negative, the graph will go down on the left and down on the right. And then I need more information to figure out what happens in the middle. Okay, on the other hand, if the degree is odd, so if the degree is even, let me summarize this by this. Let me make this a little bit larger, go a little faster with the erasing. Bear with me. I am an amateur. Okay, so if the degree is even and we have a positive leading coefficient, then the graph will go up on the left and up on the right, and I don't know what it does in the middle. But if the degree is even and I have a negative leading coefficient, it will go down on the left and down on the right, and I don't know what it does in the middle. If the degree is odd, so say for example, we have f of x equals 3x to the 5th power. then the endpoint behavior is going to be opposite. It's going to look similar to x to the third, so it'll start down on the left and up on the right. But if the degree is odd and the leading coefficient is negative, it will do the opposite. So even if I add a little more to this, plus 2x. I don't know what happens in the middle, but the graph will start up on the left and go down on the right. So just to summarize, even degrees for your largest exponent, remember, they go the same side, on the same direction on each side. Up and up for positive leading coefficients, down and down for negative leading coefficients. If the degree is odd, then the endpoints are opposite. One is down and the other one is up. If the degree is odd and the first coefficient is positive, down on the left and up on the right, just like x cubed. If the leading coefficient is negative, but the degree is odd, it's a reflection, up on the left and eventually down on the right. Okay, you're probably asking, well, what about all this stuff in the middle? What about these unknown areas in the middle here? So the second part of graphing polynomial functions, before we can do an example, is finding what we call the zeros. The zeros of a polynomial is really just another word for the X intercepts. So, for example, let me show you again on Desmos. So let's say, that we were looking at the following functions. I'm going to graph here x minus 2 times x plus 1. And what I want you to pay attention to are the x-intercepts of that red graph. The x-intercepts of that red graph are -1 from the x plus 1 and +2 from the x minus 2. Those are the x values that make the y equal to 0. That's why we call them zeros. They make your y values equal to 0. They're your x-intercepts. Okay, notice if you were to multiply this whole graph out, or the whole equation out, x minus 2 times x plus 1, your leading term would be an x squared. So this looks just like a parabola. Okay, second graph. X times x minus 3. Here, the zeros of this function are 0 and 3, and those are our x-intercepts. Now, what gets really interesting is when you have different exponents on the zeros. So watch what happens if I change this to x squared and x minus 3. I still have x-intercepts of x equals 0 and x equals 3, but what we have at 0 is called a bounce intercept. It comes up, the graph comes up, it touches the x equals 0, and then it bounces back down the same direction. What we have at x minus 3, at x equals 3, is what we call a through intercept. The graph comes up, goes through 3, and then through to the other side. The reason that x equals 0 is a bounce intercept, but x equals 3 is not, is because the multiplicity of the x equals 0 is an even number. In other words, it's x to the 2, and 2 is an even number. If we change it so that x equals 3 has a multiplicity that's even, then x equals 3 becomes our bounce intercept. So it goes through x equals 0 because the exponent is odd, but it bounces off of x equals 3 because the exponent is even. Okay, so let's capture that, and then let's practice a bunch. So the x-intercepts or the zeros. If you have x minus a to an even exponent, then x equals a is what we call a bounce intercept. And the graph would look like this. At A, it would come down, hit A, and go back up. Or it might come up to A and go back down. If, on the other hand, you have x minus A is an odd exponent, so an odd multiplicity, then x equals A is what we call a through intercept. So the curve will go through x equals A, but not bounce and go back the other direction. Might come from the bottom and then go up, or it might come from the top and then go down, but one of those two possibilities. Let me make my A a little bit better here. Okay, let's try some of these. First one, let's do f of x equals 4 times x minus 3 times x plus 4 times x minus 1. I could direct you to multiply that whole thing out, and if you were to do that, you would get 4x cubed minus 52x plus 48. Not very enjoyable, and it doesn't give us a whole lot of information about that. Besides, all we're really interested in, if we were to multiply that all out, is the power function, is the first term right there. That's all we're really interested in. So generally, when you're multiplying these out to find the power function, you just want to do the first term in each one of them. 4 times x times x times x. In other words, 4x cubed. So I'm going to erase this. And here's what we want to write down. The degree of this would be 1, 2, 3 x's. So the degree is 3, which is important that it's an odd number. Since our power function is just the most powerful term, so it would be 4x cubed, this is going to look just like x cubed. So it's going to go down on the left and up on the right. And again, I don't know what it does in the middle, so I'm not going to fill that part in. The way we know what the zeros are, tell us what does happen in the middle. So I know it goes down on the left and up on the right, and the zeros are our x intercepts. In this problem, let's see, let me highlight these. This would give us x minus 3 would give us x equals 3. Whoops. X plus 4 would give us x equals negative 4, and x minus 1 would give us x equals 1. So we have x equals 3, x equals negative 4, and x equals 1. And I want you to notice that all of the exponents on those parentheses are odd. They're all ones, so they are all what we would call through intercepts. So here we go. Let's plot those x-intercepts. X equals 3. 1, 2, 3. X equals negative 4. 1, 2, 3, 4. And x equals 1. When I draw my curve, I have to make sure that I follow all of these rules. Starting down here on the left-hand side, going through all of the intercepts and not bouncing off of them, and ending up on the right-hand side. There should only be one way to draw that graph. So we'll start down here, through negative 4, through 1, through 3, and end up going up on the right-hand side. It's a halfway decent graph of that polynomial. Okay, let's do another one. Let's graph 3x times x minus 1 to the fourth and x plus 2 to the third. So the first thing you want to look at is your power function, your degree, and your endpoint behavior. So I always do this. To find the power function, which I'll put here in red, 3x times x to the fourth times x cubed will give us the most powerful term in each part of our graph. So that would give us 3, 1 plus 4 is 5, plus 3 is 8, 3x to the 8th. So the degree is 8. The power function is 3x to the 8th, which is again positive. So this graph is going to look like x squared, up on the right and up on the left. I don't know what it does in the middle. That's what the zeros are for. Okay, to find the zeros, or the x intercepts, we're going to look at what x values, that's not what I wanted, what x values make each part of these equal to 0. So it looks like, let me erase a little bit here. Okay, it looks like we've got in green x equals 0, x equals 1, and x equals -2. So the x equals 0 for our x-intercept has an exponent of a 1 on it. So this would be a through intercept. The x equals 1, on the other hand, has an even exponent on it. So this would be our first bounce intercept. And then finally, x equals -2 has an odd exponent on it. So this would be another through intercept. Okay, so the through and the bounce and the through comes from looking at the exponents, whether they're even or odd. The through for x equals 0 from the exponent of a 1, which is odd. The bounce for the x equals 1 came from the exponent of the 4, which is even. And the through for -2 came from the exponent on the -2, which is an odd 3. Okay, putting all of that together, let's graph the x-intercept. So, whoops, here's 0. Here's +1. And here's -2. And +1 is a bounce, and the other two are throughs, which I'll denote throughs with T's and bounce with B. And then we had our endpoint behavior, so up to the left and up to the right. And there should only be one way to draw a graph that does this. Starting up here, up on the left, we have to go through x equals -2. So through x equals -2. We have to hit x equals 0, so back up, but through x equals 0, and then we bounce off of x equals 1 and end up going back up. Okay, let's try another one. All right, in this one, let's look at our power function. We have, for the power function, -5x squared times x times x to the third. So that will give us -5 times 2 plus 1 is 3 plus 3 more is 6. So the degree is 6. And our power function of -5x to the 6 means we're going to be going the same direction because it's an even exponent. But because of the negative leading coefficient, we're going down on each side. Okay, moving to the zeros. The zeros are given by x equals 0, which has a multiplicity or degree 2, so this is a bounce. X equals 4, which has a multiplicity of 1, or an exponent of 1, which is odd. So that's a through. And then x equals -2, multiplicity 3, or exponent 3, that's an odd, so that's another through. So writing that over here, x equals 0 is a bounce intercept, x equals 4 is a through intercept, and so is x equals -2. Again, when we determine that is just getting lazy. When we determine that, we're looking at the exponents on the parentheses. So let's plot those. So we've got 0, and I'll label that B for bounce. 1, 2, 3, 4, and I'll label that T for through, and -2, and I'll label this also T for through. And I got to keep in mind my endpoint behavior, so it says down on the far left and down on the far right. And there should only be one way to draw this, so I've got to go starting down on the far left through -2, bounce off of 0, and then through 4. And we're done. Last example. -2x to the 5th times x plus 1 squared times x minus 3 to the 4th. So let's see, the power function for starters. -2x to the 5th, x squared. So don't forget to include those exponents when you're doing your power function, and then x to the 4th. Those are the most powerful pieces of each part of your polynomial. So this is -2x to the 5 plus 2 is 7, plus 4 is 11. Holy cow. So the degree is 11. Your power function is -2x to the 11th. And what we care about is that the 11 is odd. So the endpoints will be different. And it's a negative, so it's going to start up, going up on the left and down on the right. And the zeros will tell us what happens in the middle. So moving to the zeros. Let's see, let me erase this. Cool. Okay, moving to the zeros, we have x equals 0, odd exponent, so it's a through. X equals -1 has an even exponent, so it's a bounce. And x equals 3 has an even exponent, so it is also a bounce. So I'll write that over here. X equals 0 is a through intercept. -1 is a bounce intercept. And 3 is a bounce intercept. Okay, so let's label those. So we have through, whoops, how about we do what we did before? Just put a T there for through. -1 is a bounce, and +3 is also a bounce. And according to our power function with the odd exponent, we start up on the far left and we end up down on the far right. Okay, so come down to -1 and bounce and go through 0 and then bounce at 3, and we should be good, ending up down to the right.